Okay, so now we'll be talking about chapter 24. We'll be talking about magnets and electrodynamics. And I'll probably be telling you some things that you already know. We know that magnets can attract or repel, and there's probably a north side and a south side. And more likely than not, there's probably some field that surrounds a magnet, and we're going to call that a magnetic field. I'll talk about how we can actually create a magnet by talking about something called domains. I will go ahead and talk about electromagnets and how electric currents can cause magnetic fields, and also a moving charged particle, which is like a current, can also experience a force in a magnetic field. I'll finish off by talking quite a bit about Earth's magnetic field and biomagnetism. So here's kind of something we know about magnets. It turns out that the Greeks discovered them, and we've been playing with magnets for over 2,000 years. They found these special stones, and these stones called lodestones could either be attracted or repelled to other lodestones, as well as to pieces of iron. Now, the Chinese, of course, were the first people to use magnets in navigation, and they used them in about the 12th century or so to create compasses, which is kind of used for navigation as we sail across oceans. So here's some things that we know about magnets. We know that magnets can either attract or repel each other. And it turns out that they can stick to certain metals, but not all metals. It turns out that metals actually have to be something called ferromagnetic. And an example of one that would be ferromagnetic would be iron. Something that would not be ferromagnetic would be something like aluminum. Of course, the Earth does seem to affect compasses, and magnets affect compasses, so magnets or compasses are probably magnets. And sometimes we can operate magnets using electricity. For example, if we're working in a scrapyard or something like that and you want to pick up a bunch of metal, then it would be great if you could turn a magnet on and off, and it turns out we can actually do that, and we're going to call that an electromagnet. So let's just kind of take a quick step back and talk about the last chapter. Something that we know about charged particles is we could have, say, a positive charged particle and a negative charged particle, and they could attract each other, or we could have a positive and they repel, and it seems to depend on how much charge as well as how far apart they are. But it turns out that this is not quite the whole story, and magnets and charges are actually quite different. So if we were to just consider for a second, suppose I had a magnet, and magnets are going to have a north side and a south side, and here I would put a south side and a north side, then what we would say is we'd actually say that in some aspects magnetic poles are like electrical charges, because here we're going to have the north and the south, and so they're probably going to attract. And what we can kind of say is like poles are going to repel and opposites are going to attract, just like with electrical charges. If I were to flip this thing around and put a north here and a south here, and go ahead and put a north here and a south here, then obviously they would repel because the north sides are closer. So proximity does seem to make a difference with magnets as well. Now, some of the differences is we can talk about magnetic poles, and when I talk about a pole, I'm talking about either the north or the south. And with magnets, they're different than charges because we cannot have one pole existing without the other pole. And there's a special name for this. This is called no monopoles. And if you've ever watched Big Bang Theory, they went on a search for a magnetic monopole in one of the earlier seasons. So no single pole has ever been found, and the person who discovers it will be a very rich person. So if we were to think about a bar magnet, we would always have a north and a south. We're never ever going to have a north and a north, or just a south. So every magnet are going to have poles at each end. We could talk about a bar magnet like this, or a horseshoe magnet. Either way, there's still going to be a north and a south. Also, similar to electrical charges, we know that there's a field that probably surrounds magnets. And when we talked about electrical charges, we talked about our electric field, or our E field, and we kind of drew it going away from positive charges and going towards negative charges. And it turns out that magnets are going to have a field that surrounds them as well, and it's going to go away from the North Pole and towards the South Pole. So it's going to go like this and like this. Now, the interesting thing with magnets is actually this is going to wrap around, because we're never going to have the north without the south. And we can talk about these magnetic field lines, and I'm going to use the symbol B to mean magnetic field. So what we can kind of do is we're kind of treating the north like the positive, where the field line goes, where the fields go away from it, and the south like the negative. Don't ask me why I didn't make the world, I just try to live in it. We're going to have these magnetic field lines that kind of wrap around from the north to the south. And not surprisingly, if I were to bring another magnet in right here, then it can interact with these magnetic field lines, and actually it's going to have its own magnetic field lines. The direction that this field points is going to be the direction that the force on a north pole would feel. So, take into account that if I didn't have a no magnetic monopole rule, if I put a north right here, it's going to feel a force in that direction. And similarly, if I put a south right here, then it's going to feel a force in the opposite direction, because we're saying north is positive and south is negative. Now, what do these magnetic field lines do? Well, if there's another another magnet that we bring into a magnetic field, then it's going to feel an influence, and it's probably going to feel a force. The shape of the line, or kind of the way that I drew, and it always goes from the north to the south, and it could also hook up to other magnets, as you'll see in a little bit. Direction is always from the north to the south, and there's some things going on with the charges inside of atoms that are kind of dictating why we call it positive and why we call it negative as such. Now, it turns out that we can actually visualize these magnetic field lines, and I don't recommend you do this because it is a pain in the butt to clean off. But if we were to take a regular bar magnet with a north and a south, and if I were to just take some iron filings, that you can kind of see with the little silvery things right here, if I were to throw that down on top of the magnet, then what you're kind of seeing is that you're seeing these lines that kind of wrap around, and these lines are actually going to be lines of constant magnetic field, and kind of how tightly these guys are packed together are going to indicate the strength of the field. So you can kind of see right here by the south pole, they're really tightly packed in, and the same over here by the north pole. And probably not surprisingly, the closer you are to a magnet, the more likely you are to feel a force from it. The further apart the lines are, the weaker the magnetic field. So if you look out here, the lines are pretty far apart, and if we brought in a magnet over here, it's not really going to be influenced nearly as much as one that was close. Now, we can also kind of visualize these field lines by just taking a look at this magnet right here. This is one of my PhET simulations that I like to play around with. And essentially, all of these little teeny tiny compasses act kind of like iron filings. You can kind of see as I move this compass right here, which is essentially a magnet, it's going to line itself up such that the north is attracted to the south and the south is attracted to the north. Something else that's kind of interesting inside of this magnet, or with the simulations, you can actually see inside of the magnet. And you can kind of see inside right here, we actually going to have what look to be teeny tiny magnets or compasses. And actually, I'm going to give these a fancy name in a little bit. I'm going to call these magnetic domains. Something that's interesting is if I were to chop this magnet in half, I would actually be left with two magnets. You can see this with this particular illustration right here, where if we had a north and a south, and if I were to take this magnet and totally chop it in half, what I'm going to be left with is not a north over here and a south over here, because that would be a magnetic monopole, we can't separate them, but I'm actually going to be left with a north and a south and a north and a south. You can see this with the field lines. The field lines kind of wrap around right here and right here. And you can kind of see that these field lines are now wrapping between the two magnets, in addition to kind of wrapping around like that and wrapping around like that. Now, something that is kind of interesting is suppose I had some magnetic field acting like this, and if I were to take a magnet or a compass, technically I forgot to mention this, but we're actually going to call this a dipole, di meaning two, so something with two poles, that it's always going to experience a torque that's going to line it up with the field. So with my compass in the other example, the north felt a pull that way, the south felt a pull in the opposite direction, and that kind of forced this in the downwards direction. Once it rotated, past the point where it would line up with the field, the north's going to feel a force like that, the south's going to feel a force like this, and it's going to try to rotate like this, and it'll kind of whip around back and forth until it eventually totally lines up with the field. Really quickly, while we're on the subject of compasses, I'll come back to these in a little bit, but I do want to talk about Earth's magnetic field and to tell you something that's going to kind of mess with you. But what we call the geographic North Pole is actually a magnetic South Pole. So technically, it's going to be a south up here and a north right there. Why we call it north? Well, when we take our compass, it's going to line up right here such that the north is pointing up. So magnetically, it's actually a south pole. Geographically, it's actually a north pole. So it might look a little bit more like this as opposed to the way that you might. Now, before I go on and talk about how magnets actually work, I do want to point out one more similar quality that magnets have to electric fields that we're already kind of familiar with, and that's that we can induce poles onto something that is neutral. Kind of like we could do that with electric fields, and I called it charge polarization. Sticking the balloon to the wall, in other words. So we could take a magnet with a north and a south, and you should fix my spelling of neutral right here. And what can happen is we could induce a north pole over here and a south pole over here, and we can essentially extend the magnet. And even if I were to take another one, that would induce a north here and a south here, and at the end of the day what I would be left with is a south. But it turns out that we can only do it with certain metals. We can't do it with all metals, and that's kind of interesting. Now, this phenomenon of being able to induce a magnet on something that is metallic is essentially why magnets can stick to fridges. But as I said, only some fridges. For example, if we had a piece of aluminum or we had a piece of stainless steel, these guys, it turns out that we can't induce a magnet on them. And what we're essentially doing is we're essentially forcing a north here and a south here and a north and a south and a north and a south and so on and so forth. So what's up with these? Well, it turns out that only some materials are made up of what we can treat as little teeny tiny magnets, and these are called ferromagnetic materials. Now, these materials are normally non-magnetic because these little magnets inside of them, they have a special name, they're called domains, and they're essentially randomly distributed, so it's such that one might be pointing like this, one like this, one like this, one like this, and these would all be a magnetic domain inside of a regular piece of metal, and these guys are going to essentially cancel each other out, and so this piece of neutral metal is actually going to appear to be non-magnetic, at least until you go ahead and you bring a north or a south near it. So let's just talk a little bit about why this is, and we're going to come back to our standard model of the atom. We're going to have a positively charged nucleus. We're going to have some electron that's orbiting it, just like the Earth orbits the Sun. And it turns out that this moving electron is actually going to induce a north pole, and whether it's going clockwise or counterclockwise is going to be whether it's pointing up or pointing down. And it turns out that this electron is also spinning around its axis like this. And that's also going to induce a north and a south, and the direction does kind of matter. So we're going to have a pair of electrons that maybe are spinning in the same direction, and that's going to cause a really strong magnet. If the electrons were spinning in opposite directions, then maybe it's not going to be magnetic. Maybe it's going to allow the domains to cancel each other out. Bear in mind it's the electron spin, not the revolution, that's going to be the main cause of magnetism. Now at last we can kind of put all the pieces of the puzzle together, and what we can do is we can say, let's take a look at some material. And that material is made up of atoms, and these atoms are going to be either a single atom or more likely than not groups of atoms, and they're all going to be spinning in the same direction, say in this direction right here, in this direction right here, and this direction right here. So we're going to have these clusters, and we're going to again call those guys domains, and when they're lined up we're going to have something that is magnetic. If we wanted to talk about something that was a permanent magnet, then this magnet is actually going to have all the domains lined up in the same direction. So if I had a bar magnet, then all the domains are going to point up like this, and 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 hence I'm going to get my north and I'm going to get my south. Now, we can actually magnetize just pieces of iron if we put them in a really strong magnetic field, and especially if we heat it up. Or if we were to take a material and just stroke it repeatedly with a magnet, that can also be another way to line up the domains. But we can also drop magnets, so we can put them into a strong magnetic field and demagnetize them. So that's why you have to be careful with your credit card around strong magnetic sources. So again, one way to create a permanent magnet is what we can do is we can just take a regular old hunk of metal, and we can put a magnetic field using some means that I'll talk about in a little bit, and then we can take the temperature and raise it up to the boiling point. And once we do that, then these domains are actually free to move around, and they can all line up in the same direction and actually become quite hard to become unstuck. and then you let it cool down, and lo and behold, we end up getting a permanent magnet. Now, I do want to talk a little bit about these magnetic domains and the difference between a permanent magnet and a temporary magnet. Probably not surprising, the permanent magnet, the domains are going to line up, and they're going to stay lined up once we take away that external magnetic field. A temporary magnet, yeah, sure, it's going to keep some level of magnetism, but it's going to slowly over time return to the random arrangements of domains, and it's not going to be very magnetic for a very long time. And lastly, let's just take a quick look at the magnetic domains for a couple of pieces of iron. If we had a piece of iron and it was non-magnetic, then all the domains would be pointing in random directions, and it's not going to have a north side or a south side. If we were to say, okay, somewhat these guys are going to point in the same direction, you kind of see how the norths are roughly lining up in that direction. You can kind of see there's going to be a north right here. So this piece would be slightly magnetized. We could have something that was strongly magnetized, and you can see the domains are all lined up nice and neat and pretty, just like this. We're going to have a really strong north and a really strong south. And as I showed you earlier, if we take this magnet and just chop it right in half, what we're going to do is we're still going to have a north domain right here and a south domain right here. So even when the magnet is broken into two pieces, we're not going to have a north, we're not going to have a south. We're going to have a little bit of north and a little bit of south.